Today, I am going to read the chapter Chemistry of Noble Gases of Inorganic Chemistry from the book Modern by Dr. S.P. Jahaur. Chapter 3 Chemistry of Noble Gases. The elements helium, neon, argon, krypton, xenon, and radon comprise noble gases. The group of noble gases is regarded as zero group or group 18 of the periodic table. These are the gases at ordinary temperature and do not have chemical reactivity. Due to chemical inertness, these were called inert gases. However, nowadays a number of compounds of these gases, particularly of xenon and krypton, have been prepared. This shows that these gases are not completely inert. Consequently, these gases are also noble gases instead of inert gases, which signifies that these gases have some reactivity. Because of low abundance of these gases on Earth, they have also been called rare gases. Occurrence of noble gases. The noble gases occur only as minor constituents in the atmosphere. Due to the inert nature of these gases, they always occur in a free state. Except radon, all these gases are present in atmosphere in the atomic state. The amount of noble gases present in atmosphere in percent by volume is given below. Abundance of helium is 5.24 into 10 raised to power minus 4%. Of neon, it is 1.82 into 10 raised to power minus 3. Of argon, it is 9.34 into 10 raised to power minus 1. For krypton, it is 1.54 into 10 raised to power minus 3. Of xenon, it is 8.70 into 10 raised to power minus 6. Helium is also present in natural gas to the extent of 2 to 7%. It is also present in small quantities in minerals of radioactive elements such as monazite, clavite, pitchblende, etc. Helium, neon, and argon are found in the water of certain springs. Radon is radioactive and does not occur in the free state because it decays very rapidly. Helium was first discovered in sunlight atmosphere. It is now known that helium is being constantly produced in sun's atmosphere by nucleus fusion reaction involving the formation of helium nucleus from 4 hydrogen atoms. History of discovery of noble gases. Noble gases are present mostly in the atmosphere. Their discovery is briefly discussed follows. First, discovery of argon. The main credit for the discovery of first noble gas, argon, goes to Cavendish. In 1785, Henry Cavendish performed a number of experiments to determine the composition of air. He passed repeated electrical sparks in a dry sample of air with an excess oxygen to convert nitrogen of the air into nitrogen dioxide according to the reaction. Nitrogen plus 2O2 is equal to 2NO2. The gaseous mixture containing nitrogen dioxide and unreacted oxygen was absorbed in alkaline potassium sulfate solution. He observed that a small amount of residual gas, about 1/20th of the original volume of air, was always left behind. He repeated the experiment again and every time observed small traces of residual gases which was neither oxygen nor nitrogen. He could not understand the nature of the residual gases which could not combine with oxygen. However, the observation of Cavendish remained unnoticed for over a century. In 1894, Lord Rayleigh observed that the density of nitrogen isolated from the atmosphere is about 0.47% higher than the density of nitrogen prepared in the laboratory by the thermal decomposition of ammonium nitrate, that is NH4NO2 is equal to N2 plus 2H2O. This minor discrepancy would have been ignored by many investigators. Then Rayleigh, in collaboration with Ramsay, repeated the earlier experiments of Cavendish and concluded that the residual gas contained a new gas different from nitrogen. It was examined carefully by spectroscopy and was found to be an unknown gas. The new gas was named argon. Second, discovery of helium. Helium was first detected spectroscopically by Lockyer in Sun's atmosphere in the year 1868 while examining atmosphere of the Sun during total eclipse. As a result of their investigations, they concluded a new element called helium. Later on, Ramsay in 1895 also detected the gas on Earth from the radioactive minerals cleveite. Kaiser in the same year detected helium in traces in the atmosphere. Third, discovery of neon, krypton, and xenon. Ramsay and Travers performed certain experiments on argon suspecting it to be a mixture of a number of similar constituent gases. They repeated experiments on liquefaction of air and its fractional distillation. The first fraction was found to contain new elements which gave a different spectrum. The element was called neon. Shortly afterwards, they discovered two more new elements on further fractional distillation called krypton and xenon. Fourth, discovery of radon. Radon was discovered by Dorn in 1902 as a result of the study of the disintegration products of radium. Position of noble gases in periodic table. While building up the periodic table of elements, Mendeleev had not left any space for the noble gases. Obviously, he could not imagine the existence of elements which have almost no chemical reactivity. Ramsay, the main discoverer of these gases, proposed a new group for these elements on the basis of their atomic masses and lack of chemical reactivity. This group is called L0 group of the periodic table. The 0 group also suggested chemical inertness or zero valency. Before the discovery of noble gases, there was a sudden change from the most electronegative halogens on right hand side to most electropositive alkali metals on left hand side in the periodic table. The addition of 0 group between 7E group and first E group has solved this anomaly. The position of noble gases in the periodic table was later on confirmed by Moseley, who constructed the periodic table on the basis of atomic number. The values of atomic number of noble gas strongly suggest that they should be placed after halogens and before alkali metals. General characteristics of noble gases. Electronic configuration. Except helium, the atoms of all noble gases have 8 electrons in their valence shell. The general electronic configuration of noble gases except helium may be expressed as Ns2np6. Helium has the electronic configuration 1s2. These configurations being stable, the noble gases neither have any tendency to gain or lose electrons, and therefore they do not enter into chemical combinations. It is therefore reasonable to assume that the inert nature of the noble gases is due to their stable electronic configurations. Physical properties. Some of the important physical constants of noble gases are given in Table 1 and these are discussed below. Atomic number. Helium 2, neon 10, argon 18, krypton 36, xenon 54, radon 86. Enthalpy of vaporization. Helium 0.08, neon 1.77, argon 6.5, krypton 9.0, xenon 12.6, radon 16.4. Atomic mass. Helium 4, neon 20.18, argon 39.10, krypton 83.80, xenon 131.30, radon 222. Atomic radius in angstrom. Neon 1.31, neon 1.73, argon 1.89, krypton 2.10, xenon 2.15. Ionization energy. Helium 2372, neon 2018, argon 1520, krypton 1351, xenon 1170, radon 1037. First, existence. All the noble gases are monoatomic, colorless and odorless. The monoatomic state of these gases is due to stable electronic configuration of their atoms. As a result, they are not capable of combining even amongst themselves. The monoatomic nature of these gases is confirmed by their values of Cp divided by Cv, where Cp and Cv are the molar heat capacity at constant pressure and at constant volume, equal to 1.66. It is observed that for all monoatomic gases, Cp by Cv is close to 1.66 second atomic radius. In the case of noble gases, the atomic radius corresponds to van der Waals radii. As we go down the group, the van der Waals radius increases due to the addition of new electronic shells. Third, ionization energy. The first ionization energies of noble gases are very high. This is attributed to the stable completely filled configurations of noble gases. However, the ionization energies decreases with increase in atomic number from helium to radon due to increasing atomic size. Fourth, electronic affinities. Due to the stable Ns2-Np6 electronic configurations, noble gas atoms have no tendency to accept additional electrons. Therefore, their electron affinities are nearly zero. 5. Melting and boiling points. The melting and boiling points of the noble gases are very low in comparison to those of other substances of comparable atomic and molecular masses. This indicates that there are no strong attractive forces between the atoms which may hold the atoms together in the liquid or in solid state. It has been established that only weak van der Waals forces are present between the atoms of the noble gases in the liquid or the solid state. Hence, van der Waals forces increases with the increase in atomic size of the atom, and therefore their boiling points and melting points increases from helium to radon. 6. Ease of liquefaction. The noble gases are not easily liquefied. This is due to the fact that there are only weak van der Waals forces which hold atoms together. This is also clear from the values of heat of vaporization of these gases. Due to the increase in atomic size and therefore increase in van der Waals forces, the ease of liquefaction increases down the group from helium to radon. 7. Solubility in water. The noble gases are only slightly soluble in water. The solubility in general increases from helium to radon. The solubility of noble gases in water is due to dipole-induced dipole interactions. Water is a polar molecule. When it comes near a noble gas atom, it induces dipole in the noble gas atom by distorting or polarizing the symmetrical electron cloud of noble gas atoms. As a result, the induced dipole appears on the noble gas atom, leading to interaction with the dipole polar water molecule. Therefore, because of dipole-induced dipole interactions between water molecules and noble gases atom, the noble gas dissolves in water. As the size of noble gas atom increases, the extent of polarization also increases. Consequently, the magnitude of the dipole-induced dipole interactions increases, and hence the solubility of the noble gases in water increases from helium to radon. 8th, general characteristics. In general, noble gases are not very reactive. Their inertness to chemical reactivity is attributed to the following reasons. First, the noble gases have completely filled Ns2-Np6 electronic configurations in their valence shells. Second, the noble gases have very high ionization energies. Third, the electron affinities of noble gases are almost zero. Therefore, they have neither tendency to gain nor to lose any electrons and do not enter into chemical combinations. However, in recent years, it has been found that noble gases, particularly xenon and krypton, have formed some compounds. Chemistry of compounds of noble gases. Prior to 1962, it was believed that the noble gases do not combine at all and no compounds of noble gases were formed, though from time to time some attempts have been made to test the reactivity of noble gases. Yet the gases were thought to be inert. This was also supported by the following reasons. First, the atoms have stable, completely filled electronic shells. Second, they have high ionization energies. Third, the noble gases have almost zero electron affinities. Therefore, they do not have tendency to gain, lose or share electrons with other atoms. The above reasons discouraged the chemists to make serious attempts to prepare compounds of noble gases. In 1962, N. Bartlett, while investigating the chemistry of PTF6, noticed that platinum hexafluoride PTF6 acts as a powerful oxidizing agent which combines with molecular oxygen to form ionic compounds. Dioxygenyl hexafluoride O2 plus PTF6 is equal to O2 positive PTF6 negative. This indicates that PTF6 has oxidized O2 to O2 positive. Now oxygen and xenon have some similarities, and this led Bartlett to try reaction between xenon and PTF6 in a similar manner. For example, the first ionization energy of xenon gas is comparable to that of oxygen for the process. O2 is equal to O2 positive plus electron. Second, the molecular diameter of oxygen and atomic radius of xenon are almost same. With this assumption, Bartlett reacted xenon and platinum hexafluoride in gas phase and an orange-yellow solid xenon hexafluoroplatinate of the composition XePTF6 was obtained. On analysis, this compound was found to be ionic compound Xe positive PTF6 negative, and this marked the first compound of any noble gas. Xe plus PTF6 is equal to Xe positive PTF6 negative xenon hexafluoroplatinate. Orange yellow. The formation of this ionic compound has demonstrated that xenon is not totally inert, and it is possible to remove an electron from xenon atom. This discovery attracted many scientists for active research for the preparation of other noble gas compounds. Within a few months, XeF4 and XeF2 have been prepared in laboratories. Thus, noble gas chemists began among these noble gases. Xenon forms a large number of compounds with fluorine or with oxygen, and krypton forms only a few compounds. Some important stable compounds of xenon in different oxidation states are oxidation state +2 compounds XeF2 xenon difluoride, oxidation state +4 XeF4 xenon tetrafluoride, and XeOF2 xenon oxydifluoride. Oxidation state +6 XeF6 xenon hexafluoride, XeOF4 xenon oxytetrafluoride, XeO2F2 xenon dioxyfluoride. Oxidation state +8 XeO8 xenon octaoxide, XeF8 xenon octafluoride, XeO4 xenon tetraoxide. Before discussing the chemistry of compounds of noble gases, it becomes important to understand the answers of some important questions. First, what are the factors responsible for late discovery of compounds of noble gases? Second, why do most of the compounds involve xenon, fluorine, and oxygen? Late discovery of compounds of noble gases. Prior to 1962, it was believed that noble gases do not combine because they have stable electronic configurations. Many attempts were made to prepare their compounds, but all these attempts proved to be unsuccessful. Moisen in 1895 had reported that there was no chemical reactivity between fluorine and argon. This led Ramsay to conclude that the noble gases are chemically inert. This conclusion was also supported by the concept of valency. According to the concept of valency, the electronic configuration having 8 electrons in its valence or outermost shell has been taken as a criteria of stability and inertness. That is why the noble gases were assigned zero valency, and this group was designated as zero group. However, the concept of octet configuration of noble gas suffered setback because of discovery of compounds like PF5, SF6 and IF7, which had more than 8 electrons in their valence shell. This, however, did not make the scientists to make more serious attempts because of noble gases seemed to have neither any tendency to lose electrons nor any tendency to gain electrons. Some other factors in addition to chemical inertness of noble gases which lead to late discovery of noble gases compounds are: first, lack of availability of fluorine of good quality. Second, non-availability of fluorine resistant greases. Third, non-availability of inert material to handle fluorine gas. Fourth, non-availability of large quantities of noble gases. Why do most of the compounds involve xenon, fluorine, and oxygen? We know that the tendency of an atom to lose electron is given by its ionization energy. If we see carefully, the ionization energies of these elements are given in table 1. It is noticed that leaving aside radon, which is unstable, only xenon and to some extent krypton has ionization energy comparable with some elements like carbon, nitrogen, and oxygen. Xenon therefore has the maximum tendency to lose electrons and thus forms the largest number of compounds. Krypton comes next. Neon, argon, and helium, which have much higher ionization energies, form hardly any compounds. Further, since reactivity of xenon and krypton is due to the tendency to lose their electrons, it suggests that the combining atom should have strong affinity for electrons, that is, should be strongly electronegative. Now, in the periodic table, fluorine and oxygen have high electron affinities and therefore have strong tendency to accept electrons from other atoms. It is for this reason that xenon and krypton form compounds mostly with strong electron acceptors, which fluorine and oxygen. The most of these compounds are fluorides, oxyfluorides, and oxides. Xenon combines directly with fluorine. Its compounds with oxygen are obtained from its difluorides. Xenon chloride is known, but it is not stable. Only one compound with nitrogen is known, but it is highly unstable. Compounds of xenon. Xenon forms a large variety of compounds with fluorine and oxygen in different oxidation states. These are xenon fluoride, xenon oxide, and xenon oxyfluorides. Let us discuss the methods of preparation, the stereochemistry and important properties of these compounds. Xenon plus 2 compounds. First, xenon difluoride, XeF2. Preparation. It can be prepared by the following methods. First, xenon fluoride is the best prepared by heating a mixture of xenon and fluorine in molecular ratio of 2:1 at 400 degrees Celsius in a sealed nickel tube. On cooling quickly, a colorless solid XeF2 is obtained. Xe plus F2 in presence of nickel and 400 degrees Celsius is equal to XeF2. Excess of xenon is used to avoid formation of any higher fluorides such as XeF4. Second, it can also be prepared by subjecting a mixture of xenon and fluorine in a molecular ratio 2:1 to electric discharge. Xe plus F2 in presence of electric discharge is equal to XeF2. 3. It is also formed by photochemical combinations of xenon and fluorine in the presence of mercury vapors. Xe plus F2 in presence of mercury vapor is equal to XeF2. Fourth, it can also be prepared quantitatively by fluorination of xenon by oxygen monofluoride O2F2 at -78 degrees Celsius. Xe plus O2F2 minus 78 degrees Celsius is equal to XeF2 plus O2. Properties. First, xenon difluoride is colorless crystalline solid which melts at 129 degrees Celsius. Second, it is the least volatile xenon fluorides. It is stable in pure and dry state and can be stored in nickel containers. Third, it dissolves in hydrogen fluoride without reacting with it. Fourth, it reacts with hydrogen to give hydrogen fluoride and xenon. XeF2 plus H2 is equal to Xe plus 2HF. Fifth, it gives substitution reactions with strong protonic acids. XeF2 plus HX is equal to FXEX plus HF. FXEX plus HX is equal to XeX2 plus HF, where X is equal to ClO4 negative, CF3COO negative, SO3F negative, etc. Sixth, it hydrolyzes slowly but completely in acidic and neutral or alkaline solutions. 2XeF2 plus 2H2O is equal to 2Xe plus 4HF plus O2. 2xEF2 plus 4NaOH is equal to 2xe plus 4NaF plus O2 plus 2H2O. 7th, it oxidizes iodine in presence of BF3 to give IF. XeF2 plus I2 is in presence of BF3 is equal to 2IF plus Xe. 8. It reacts with nitrogen monoxide and nitrogen dioxide. XeF2 plus 2NO is equal to 2NOF plus Xe, nitrosyl fluoride. XeF2 plus 2NO2 is equal to 2NO2F plus Xe. 9. It reacts with sulfur trioxide to give xenon. XeF2 plus 2SO3 is equal to Xe plus S2O6F2, that is peroxy disulfuryl difluoride. 10th, it is a mild fluorinating agent, thus it reacts with benzene to give fluorobenzene, C6H5F. It also fluorinating ethylene to 1,1-difluoroethane. Ethylene plus XeF2 in solid state is equal to 1,1-difluoroethane plus Xe gas. 11th, it is also a strong oxidizing agent. It oxidizes HCl to Cl2, cesium plus 3 to cesium plus 4, chromium plus 3 to chromium plus 4, and BrO3 negative to BrO4 negative. BrO3 negative plus XeF2 plus H2O is equal to Xe plus BrO4 negative plus 2HF. 12. Xenon fluoride difluoride in anhydrous hydrogen fluoride reacts readily with platinum metal, sulfur powder, and iridium to produce highest fluorides. Pt plus 3xEF2 is in presence of HF is equal to PtF6 plus 3xe. S8 plus 24xEF2 in presence of HF is equal to 8SF6 plus 24xe. 10IR plus 5xEF2 in presence of HF is equal to 10IRF5 plus 5xe. 13th, in BrF2 solution, xenon difluorides acts as a Lewis base and forms adducts with composition XeF2.mF5, XeF2.2mF5 and 2xeF2.mF5, where M is equal to phosphorus, arsenic, antimony, etc. For example, XeF2 plus SbF5 is equal to XeF2 dot SbF5. XeF2 plus AsF5 is equal to XeF2 dot AsF5. These compounds XeF2 dot SbF5 and XeF2 dot AsF5 exists as ionic species as XeF positive SbF6 negative and XeF positive AsF6 negative respectively. Similarly, XeF2 plus 2SbF5 is equal to XeF2 dot 2SbF5. The compounds XeF2 dot 2SbF5 has been shown to contain XeF positive and Sb2F negative ions. The XeF positive ion is strongly bonded to Sb2F11 negative by a fluoride bridge between Xe and Sb. The ions contains two octahedra linked by a shared F as shown ahead. XeF2 also reacts with arsenic pentafluoride in a different stoichiometry. 2xeF2 plus AsF5 is equal to 2xeF2 dot AsF5. 2xeF2 dot AsF5 exists as Xe2F3 positive, AsF6 negative. The ion Xe2F3 positive has the expected linear geometry around xenon and an angular geometry around the xenon fluoride. Structure and shape of xenon fluoride molecules. Spectroscopy analysis has shown that XeF2 molecule has a linear geometry. This is explained on the basis of valence bond theory as follows. Xenon in the ground state has the valency shell configuration 5s2 5p6 as shown in the figure. One of the 5p electrons gets unpaired and promoted to the 5d orbitals, resulting in two unpaired electrons. One in 5p and one in 5d orbital. In the excited state of xenon, 5 orbitals, one 5s, 3 5p and one 5d, hybridize to give sp3d hybrid orbitals, which adopt trigonal bipyramidal geometry. The two orbitals containing single electron overlap with two fluorine atoms forming two XEF bonds. The xenon and two fluorine atoms lie in a straight line, that is, are linear. While the equatorial positions are occupied by three lone pair of electrons, the molecule has thus a linear geometry, as shown in the figure. The lone pairs are present on equatorial positions of the triangle in a plane. Because of the symmetrical arrangement of three lone pairs, each at an angle of 120 degree, the net repulsions on bond pairs is 0. Therefore, XeF2 molecule is linear. The important properties of XeF2 are summarized below. Xenon plus 4 compounds. Second, xenon tetrafluoride, XeF4. Preparation. It can be prepared by the following methods. First, it is prepared by good yield by heating a mixture of xenon and fluorine in the molar ratio 1:5 in a nickel vessel at 400 degrees Celsius under a pressure of 5 to 6 atm. Xe plus 2F2 in presence of 400 degrees Celsius and at 5 to 6 atmospheric pressure is equal to XeF4. Second, it is also synthesized by passing an electric discharge through a mixture of xenon and fluorine in molar ratio of 1:2 at minus 78 degrees Celsius. The pressure is maintained between 2 to 15 mm of Hg. Xe plus 2F2 in presence of electric discharge and minus 78 degrees Celsius is equal to XeF4. Properties. The important properties of XeF4 are: first, it is a colorless crystalline solid. Second, its melting point is 117.1 degrees Celsius. It sublimes readily. Third, it dissolves in iodine pentafluoride and hydrogen fluoride without reacting. Fourth, it is oxidized by hydrogen to HF at 30 degrees Celsius. XeF4 plus 2H2 is equal to Xe plus 4HF. Fifth, it is a stronger fluorinating agent than XeF2. It converts Hg to HgF2, Pt to PtF4, NO to NO2 to NOF, and NO2F, SF4 to SF6, etc. For example, 2Hg plus XeF4 is equal to Xe plus 2HgF2. Pt plus XeF4 is equal to Xe plus PtF4. 2SF4 plus XeF4 is equal to Xe plus 2SF6. Sixth, it reacts with boron trichloride to form boron trifluoride. 3XeF4 plus 4BCl3 is equal to 4BF3 plus 3Xe plus 6Cl2. 7. It undergoes disproportionation in water readily, a highly explosive solid compound XeO3. 6XeF4 plus 12H2O is equal to 4Xe gas plus 2XeO3 solid plus 24HF aqueous plus 3O2. But if the reaction is controlled at minus 80 degrees Celsius, it forms xenon oxyfluoride. XeF4 plus H2O at minus 80 degrees Celsius is equal to XeOF2 plus 2HF. 8. It combines with molten TaF5 to form straw-colored XeTaF6 whole twice. XeF4 plus 2TaF5 is equal to XeTaF6 whole twice plus F2. 9th, it forms an addition compound with antimony pentafluoride. XeF4 plus SbF5 is equal to XeF4 dot SbF5 or XeF3 positive SbF6 negative. XeF4 plus 2SbF5 is equal to XeF4 dot 2SbF5 or XeF3 positive Sb2F11 negative. XeF3 positive has T-shaped structure, that is trigonal bipyramidal, with two positions occupied by lone pairs as shown below. Structure. The electronic structure of XeF4 may be written as: spectroscopic method has shown that XeF4 has square planar structure. This can be explained on the basis of valence bond theory as described below. Xenon atom in the ground state has 5s2 5p6 outer shell electronic configuration. In the formation of XeF4 molecule, two of the 5p electrons are promoted to 5d orbitals, so that there are now 4 unpaired electrons. The 6 orbitals 1 5s, 3 5p and 2 5d get hybridized to form 6 sp3d2 hybrid orbitals. These 6 sp3d2 hybrid orbitals adopt octahedral geometry. 4 of these containing single electron overlap with 2p orbitals of fluorine to form 4 XeF bonds. The remaining 2 positions are occupied by lone pairs. Thus, as shown in figure 3, the molecules has a square planar shape. Third, xenon oxyfluoride, XeOF2. Preparation. It is prepared by slowly and partial hydrolysis of XeF4 at a low temperature, minus 80 degrees Celsius. XeF4 plus H2O is equal to, at minus 80 degrees Celsius, is XeOF2 plus 2HF. It is not a very stable compound. Structure. Spectroscopic method have shown that xenon oxidifluoride has T-shaped structure. This can be explained on the basis of valence bond theory as described below. Xenon atom in the ground state has 5s2 5p6 outer shell electronic configuration. To account for tetravalency to xenon, 3 sigma bonds and 1 pi bond. 2 of the 5p electrons are promoted to the 5d orbitals in excited state as represented in figure 4. In this case, the 5 orbitals 1 5s, 3 5p and 1 5d get hybridized to form 5 sp3 hybrid orbitals. 1 5d orbital is left unhybridized for forming pi bonds. 3 of the 5 hybrid orbitals which are singly filled form sigma bonds with 2 fluorine and 1 oxygen atoms. 1 5d orbital which is not involved in hybridization and is singly filled is used in forming an additional bond which is pi bond. With the oxygen atom, there is thus a double bond, 1 sigma bond and 1 pi bond between xenon and oxygen atoms. Since the XeOF2 molecule involves sp3d hybridization, its structure should be trigonal bipyramidal, but due to the presence of 2 lone pairs of electrons occupying 2 positions in the structure, there is distortion in the molecule. The compound therefore has a T-shaped structure as shown in figure. Fourth, xenon plus 4 compounds. Xenon hexafluoride, XeF6. Preparation. It is prepared by the following methods. First, it is prepared by heating xenon with excess of fluorine in the molar ratio of 1:20 in a nickel vessel at 250 to 300 degrees Celsius under pressure of 50 to 60 atm. Xe plus 3F2 is equal to XeF6. Second, it can also be obtained by the oxidation of XeF4 with O2F2 under pressure. XeF4 plus O2F2 at minus 30 degrees Celsius is equal to XeF6 plus O2. Third, it is also prepared by passing electric discharge through a mixture of xenon and fluorine in the ratio of 1:3 at low temperature. XeF6 can be separated from XeF2 and XeF4 by passing through NaF, which absorbs XeF6 at 70 degrees Celsius, giving Na2XeF8. XeF6 plus 2 NaF at 17 degrees Celsius is in equilibrium with Na2XeF8. On warming Na2XeF8 at 120 degrees Celsius, pure XeF6 is evolved. Na2XeF8 at 120 degrees Celsius is equal to XeF6 plus 2 NaF. Properties. It is a solid crystalline substance. Second, it melts at 49.5 degrees Celsius. Third, it is most volatile of all fluorides of xenon. Its vapor have a greenish yellow color. 4. It dissolves in hydrogen fluoride, giving a solution which is a good conductor of electricity. This is attributed to the formation of ions under HF plus XeF6 is equal to XeF5 positive plus HF2 negative. XeF6 thus differs from XeF2 and XeF4 as it dissolves in hydrogen fluoride without reaction. 5. It is reduced to xenon by the action of H2NH3 or HCl. XeF6 plus 3H2 is equal to Xe plus 6HF. XeF6 plus 8NH3 is equal to Xe plus 6NH4F plus N2. XeF6 plus 6HCl is equal to Xe plus 3Cl2 plus 6HF. 6. It undergoes slowly hydrolysis with atmospheric moisture and forms XeO3 which is highly explosive. XeF6 plus 3H2O is equal to XeO3 plus 6HF. Careful hydrolysis in a nickel vessel give colorless stable liquid XeOF4. XeF6 plus H2O is equal to XeOF4 plus 2HF. 7. It is extremely reactive, therefore it cannot be stored in glass or quartz vessel because of the following reactions, which is finally giving the dangerous explosive xenon trioxide. 2XeF6 plus SiO2 is equal to 2XeOF4 plus SiF4. 2XeOF4 plus SiO2 is equal to 2XeO2F2 plus SiF4. 2XeO2F2 plus SiO2 is equal to 2XeO3 plus SiF4. XeO3 which is explosive. 8th, it reacts with fluoride ion acceptors to form adducts. XeF6 plus PtF5 is equal to XeF6 dot PtF5 is equal to XeF5 positive PtF6 negative. XeF6 plus SbF5 is equal to XeF6 dot SbF5 is equal to XeF5 positive SbF6 negative. XeF5 positive has square pyramidal geometry as shown below. 9th, with fluoride ion donor it forms XeF7 negative and XeF82 negative species. CSF plus XeF6 is equal to CSF dot XeF6 is equal to CS2 XeF8. 2RbF plus 2XeF6 at 20 degrees Celsius is equal to 2RbXeF7 at 50 degrees Celsius is equal to Rb2XeF8 plus XeF6. XeF62 negative ion has square anti-prismatic structure and shape of XeF6 molecule. The ground state outer shell electronic configuration of xenon is 5s2 5p6. 3 of the 5p electrons are promoted to the 5d orbitals so that there are 6. 5. Formation of XeF6 molecule involving sp3d3 hybridization. The dotted arrow represents electrons supplied by fluorine atoms. Unpaired electrons 3 in 5p orbital and 3 in 5d orbital. In this case, 7 orbitals 1s, 3p and 3d hybridize to give 7 sp3d3 hybrid orbitals, which adopt pentagonal bipyramidal geometry. 6 of these orbitals containing single electron each are used in bonding with 6 atoms of fluorine. Due to sp3d3 hybridization, the molecule should have pentagonal bipyramidal structure, but it is slightly distorted on account of the presence of a lone pair of electrons in one position, as shown in figure. However, there has a controversy regarding its structure. It is preferably believed to have a distorted octahedral structure in which all the 6 positions are occupied by fluorine atoms and the lone pair is present at the center of one of the triangular faces. This is shown in figure. Alternatively, it has been suggested that the lone pair is present in the middle of the edge. The chemical properties of XeF6 are summarized. 5. Xenon oxytetrafluoride XeOF4 preparation. It can be prepared by the following methods. First, xenon oxytetrafluoride is prepared by partial hydrolysis of xenon hexafluoride. XeF6 plus O2 is equal to XeOF4 plus 2HF. Second, it can be prepared by the action of XeF6 on silicon dioxide. 2XeF6 plus SiO2 at 50 degrees Celsius is equal to XeOF4 plus SiF4. Soon as the yellow color of XeF disappears, the contents are immediately quenched with solid CO2. It is done to avoid the formation of XeO3, that is explosive, as XeOF4 plus SiO2 is equal to XeO3 plus SiF4. Third, it is prepared in appreciable quantities by heating a mixture of xenon and fluoride in the molar ratio of 1:4 in the presence of a large excess of oxygen at about 230 degrees Celsius. It can be purified by vacuum distillation. Xe plus O2 plus 4F2 is equal to 2XeOF4. Properties. It is a colorless compound melting at minus 46 degrees Celsius. Second, it is reduced by hydrogen to xenon. XeOF4 plus 3H2 is equal to Xe plus H2O plus 4HF. Third, it reacts with water or silica to form another oxyfluoride XeO2F2 in which xenon remains in the same oxidation state. Further, reactions giving explosive compounds XeO3. XeOF4 plus H2O is equal to XeO2F2 plus 2HF. XeO2F2 plus H2O is equal to XeO3 plus 2HF. 2XeO4 plus SiO2 is equal to 2XeO2F2 plus SiF4. 2XeO2F2 plus SiO2 is equal to 2XeO3 plus SiF4. Fourth, it reacts with F-negative ion acceptors to form XeOF3 positive cation. XeOF4 plus SbF5 is equal to XeOF3 positive plus SbF6 negative. XeOF4 plus 2SbF5 is equal to XeOF3 positive plus Sb2F11 negative. The XeOF3 positive cation has the following structure in which the lone pair, the oxygen atom and the fluorine atom occupy the equatorial positions of the trigonal bipyramidal structure and two fluorine atoms occupy axial positions. 5. XeOF4 reacts with nitrosyl fluoride to give a crystalline compound NO positive, XeOF5 negative. XeO4 plus NOF is equal to NO positive, XeOF5 negative. XeOF5 negative ion has pentagonal pyramidal structure with the oxygen atom in the optical position as shown below. In this case, xenon atom is slightly above the plane of 5 F atoms. Structure and shape of XeOF4 molecule. Xenon atom in the ground state has 5s2 5p6 outer shell electronic configuration. In order to account the hexavalency of xenon in XeOF4, 3 of the 5p electrons are promoted to 5d orbitals when excited, as shown in figure. The 6 orbitals get hybridized to form 6 sp3d2 hybrid orbitals which adopt octahedral symmetry. One of the 3d electrons remain unhybridized for forming pi bonds. 5 of the singly occupied hybrid orbitals form sigma bond with 4 fluorine atoms and 1 oxygen atom. The 5d orbitals which does not take part in the hybridization forms pi bond with the oxygen atom. Thus oxygen is combined to xenon by a double bond, one of which is a sigma bond and the other is pi bond. It may be noted that one of the hybridized orbitals contains a lone pair of electrons. The molecule has a square pyramidal structure. 6. Xenon dioxide difluoride XeO2F2. Preparation. First, it is prepared by mixing XeO3 and XeOF4 at the low temperature close to minus 78 degrees Celsius. XeO3 plus XeOF4 at minus 78 degrees Celsius is equal to 2XeO2F2. The compound is purified by fractional distillation. Second, it is also formed when XeOF4 is hydrolyzed or reacted with silica. 2XeOF4 plus SiO2 is equal to 2XeO2F2 plus SiF4. XeOF4 plus H2O is equal to XeO2F2 plus 2HF. Properties. It is a colorless solid. Second, its melting point is 30.8 degrees Celsius. 3. It is easily hydrolyzed to give xenon trioxide. XeO2F2 plus H2O is equal to XeO3 plus 2HF. Fourth, it slowly decomposes to give XeF2 and O2. Therefore, thermodynamically, it is unstable. XeO2F2 is equal to XeF2 plus O2. 5. It reacts with SbF5 in HF and gives a white solid of composition XeO2F positive SbF11 negative. XeO2F2 plus 2SbF5 is equal to XeO2F positive Sb2F11 negative. This compound is unstable at room temperature and slowly decomposes to give XeF positive, Sb2F11 negative and oxygen. XeO2F negative has tetrahedral structure in which one position is occupied by a lone pair. Structure and shape of XeO2F2. In this case, 3 of the 5p electrons are promoted to 5d orbitals when excited as shown in the figure. The 5 orbitals 1, 5s, 3, 5p and 1 of the d 5d orbitals get hybridized to form 5 sp3d hybrid orbitals. These adopt trigonal bipyramidal geometry. 2 of the 5d orbitals are left unhybridized for forming pi bonds. The 4 hybrid orbitals form sigma bond with 2 fluorine atoms and 2 oxygen atoms. The remaining 2 singly filled orbitals which do not take part in hybridization forms pi bond with the same 2 oxygen atoms. Each oxygen atom is thus bonded to xenon atom by a double bond, one of which is a sigma bond and the other is pi bond. It may be noted that one of the hybrid orbitals contain a lone pair of electrons. The molecule does not have a regular geometry. There is, however, a slight distortion due to the presence of a lone pair in one of the equatorial positions. 7. Xenon trioxide XeO3. Preparation. Xenon trioxide is prepared by hydrolysis of XeF6 or XeF4. 6XeF4 plus 12H2O is equal to 2XeO3 plus 4Xe plus 6HF plus 3O2. XeF6 plus 3H2O is equal to XeO3 plus 6HF. However, the last reaction proceeds through the following stages. XeF6 plus H2O is equal to XeOF4 plus 2HF. XeOF4 plus H2O is equal to XeO2F2 plus 2HF. XeO2F2 plus H2O is equal to XeO3 plus 2HF. Great care should be taken during its preparation because it is highly explosive. Properties. First, xenon trioxide is a white non-volatile solid. Second, it is soluble in water. It is quite stable in aqueous solution. However, it explodes violently when dry. Third, it acts as a powerful oxidizing agent in acidic medium. For instance, it oxidizes Pu3 positive to Pu4 positive in presence of H positive ions. 6 Pu3 positive plus XeO3 plus 6 H positive is equal to 6 Pu4 positive plus Xe plus 3H2O. The advantages of this reaction is that the only byproduct is xenon gas, which being inert does not introduce any extra complicating reaction. It also reacts with potassium iodide, giving 3 moles of iodine per mole of xenon trioxide. XeO3 plus 6I negative plus 6H positive is equal to Xe plus 3I2 plus 3H2O. 4. It undergoes disproportionation when dissolved in sodium hydroxide and forms sodium perxenate Na4XeO6.H8H2O. 2XeO3 plus 4NaOH plus 6H2O is equal to Xe plus O2 plus Na4XeO6.8H2O. The X-ray analysis of sodium perxenate reveals the existence of the octahedral perxenate ion XeO6 negative in the substance. Sodium perxenate, when dissolved in an acid solution, decomposed slowly to give XeO3 and oxygen. Na4XeO6 plus 4HCl is equal to 4NaCl plus H4XeO6. 2H4XeO6 is equal to 2XeO3 plus 4H2O plus O2. 5. It reacts with XeF6 and XeOF4. XeO3 plus 2XeF6 is equal to 3XeOF4. XeO3 plus XeOF4 is equal to 2XeO2F2. Structure and shape of XeO3 molecule. Xenon in the ground state has the outer shell electronic configuration as 5s to 5p6 as shown in figure. In the formation of XeO3, 3 of the 5p electrons are promoted to 5d orbitals. The 4 orbitals 1, 5s, 3, 5p hybridized to form 4 sp3 hybrid orbitals which adopt tetrahedral geometry. 3 electrons on xenon remains unhybridized for forming sigma bonds. 3 of the 4 hybrid orbitals which are singly filled form 3 pi bonds with 3 oxygen atoms. The 3 unhybridized 5d orbitals form 3 pi bonds with the same 3 oxygen atoms. Thus, each oxygen atom is bonded to xenon by a double bond, one of the hybrid orbitals containing a lone pair of electrons. Consequently, the molecule instead of being tetrahedral has a pyramidal structure as shown below. Xenon plus 8 compounds. Although there have been some reports of compounds of xenon in plus 8 oxidation state, these have not been confirmed by more recent works. The common compounds suggested XeF8, XeO4, XeOF6, XeO3F2 and XeO2F4. Among these, XeFO4 has been prepared successfully. XeOF4 has been prepared by the action of concentrated H2SO4 on sodium or barium xenate. It may be purified by vacuum sublimation at -78 degrees Celsius. XeO6 4 negative plus 4H positive is equal to H4XeO6 is equal to XeO4. It is unstable and decomposes to xenon and oxygen. It is very explosive and explodes even at -40 degrees Celsius. XeO4 gaseous state is equal to Xe plus 2O2 plus 643 kJ. It has tetrahedral structure. Compounds of other noble gases. Recent experiments have shown that krypton and radon can also combine with fluorine under suitable conditions, yielding krypton difluorides KrF2 and krypton tetrafluorides KrF4 and radon difluorides RnF2. Krypton difluorides preparation. First, it is prepared by irradiating a mixture of krypton and fluorine at a very low temperature, that is -193 degrees Celsius. Irradiation can be carried out by gamma rays, UV lights or by electric discharge. Kr plus F2 in presence of gamma rays and at -193 degrees Celsius is equal to KrF2. Properties. First, KrF2 is a colorless solid. Second, it is easily hydrolyzed. 2KrF2 plus 2H2O is equal to 2Kr gas plus O2 gas plus 4HF aqueous. 3. It is a powerful oxidizing and fluorinating agent. 4. It forms adducts with SbF5 and AsF5s. KrF2 plus SbF5 is equal to KrF2 dot SbF5 is equal to KrF positive SbF6 negative. KrF2 plus 2SbF2 is equal to KrF2 2SbF5 is equal to KrF positive Sb2F11 negative. KrF2 plus 2AsF5 is equal to KrF2 dot 2AsF5 is equal to KrF positive As2F11 negative. Structure. The structure of KrF2 is similar to that of XeF2. It also involves sp3d hybridization of 5 orbitals. 2 of these hybrid orbitals form sigma bonds with 2 fluorine atoms and 3 positions are occupied by lone pairs. The symmetry is linear as shown in the figure. KrF4 and oxides have been claimed definitely. Radon difluoride can also be prepared by similar methods. However, it is highly unstable. Are compounds of helium and neon possible? In normal state, all the s and p orbitals of xenon, krypton and radon atoms are fully filled. However, there are vacant d orbitals in their valence shell, which allow for the promotion of one or more electrons from d orbitals for the formation of unpaired electrons. If this be the case, it seems that helium and neon will never form compounds because they have no d orbitals at all. The promotion of electrons from s and d orbitals to next shell is highly favorable. Moreover, the ionization energies of helium and neon are considerably higher than those of xenon and krypton. This fact also rules out the possibility of the formation of compounds of helium and neon.